Hi! In the previous section, you have seen several examples of linear transformations. For example, you saw that any matrix transformation is a linear transformation. In this video, I will show you that the opposite is also true. Any linear transformation is, in fact, a matrix transformation. To be precise, suppose T from Rn to Rm is a linear transformation. Then there is an m times n matrix A such that T of x equals A times x for all vectors x in Rn. The matrix A does not depend on the vector x. We call this matrix the standard matrix of the transformation. Let me show you how this works by looking at an example that we saw in an earlier video. Suppose you want to rotate a vector v with components a, b by 45 degrees counterclockwise. The trick is to write v as a linear combination of the standard unit vectors. Then r of v is equal to r of a times e1 plus b times e2. And because r is a linear transformation, this is equal to a times r of e1 plus b times r of e2. The rotations of e1 and e2 are easy to find, so we get an expression for the rotation of v. Since this is a linear combination of vectors with coefficients a and b, we can rewrite it as a matrix times the vector v. This matrix does not depend on v, so you see that the rotation is indeed a matrix transformation. And the matrix we found is the standard matrix. Note that the columns of the standard matrix are precisely obtained by applying the transformation to the standard unit vectors. This illustrates how to find the standard matrix of a linear transformation. If T is a linear transformation from Rn to Rm, and we denote the standard basis vectors of Rn as e1 to en as usual, then the columns of the standard matrix are obtained by applying the transformation to each standard basis vector. The proof runs precisely analogously to the example. Take a vector x in Rn and write it as linear combination of the standard basis vectors. Then T of x can be written like this. Since T is a linear transformation, we can rewrite this as a linear combination of T of e1 to T of en, with x1 to xn as coefficients. Since this is a linear combination of vectors, we can write this as a matrix with columns Te1 to Ten times a vector with components x1 to xn. The vector is the vector x, and the matrix, which does not depend on x, is the standard matrix A. The fact that every linear transformation is a matrix transformation means that all the examples of linear transformations, like rotations, projections, and reflections, can be written as a matrix transformation. This is very important for concrete calculations, for example in computer graphics. Rotating objects might sound difficult at first, but in the end it comes down to matrix vector multiplication, and that is something computers are very good at. In the rest of the section, you will find standard matrices yourself and study the properties.